If I told you that a dirty, highly flawed, completely disordered piece of crystal could conduct electricity with, like, absolute mathematical perfection.
Right, ignoring every single physical defect inside it.
Yeah, exactly.
Yeah.
You'd probably tell me my physics is fundamentally broken. I mean, it goes against everything.
It really does. It is a profound shift in perspective. Because usually when we look at a macroscopic solid, like a block of copper or a silicon microchip.
Or even just the glass on your window, right?
Exactly. We assume it obeys these static classical rules. We assume we understand it. But the moment you zoom in, and I mean really look at the quantum mechanical underpinnings, that static reality just dissolves.
It turns into this chaotic storm of probabilities and interacting waves.
Interacting waves, collective behaviors that completely defy common sense.
And that brings us to today's mission. We are taking a deep dive into the graduate-level textbook, Electrons and Solids, by Hendrik Bloom and his colleagues from RWTH Aiken University.
It is a phenomenal text. Very dense.
Oh, incredibly dense. But for you, our listener, we aren't just giving you a standard summary today. You actually handed us a very specific challenge.
A very rigorous one, actually.
Yeah. You asked us to act as your pedagogical coaches, breaking this text down chapter by chapter into a highly structured framework.
Which we love.
We absolutely love a structured challenge. You want the big ideas, the advanced deep dives, the connective tissue, practical recaps, and critical thinking challenges. So we are delivering exactly that for you today.
It's a great way to tackle a book this complex.
I'll be acting as your proxy, keeping us on track and moving us through the structure. But before we jump into the first chapter, we need to establish the meta theme.
Right, the overarching philosophy of this entire field of solid-state physics. To understand any of this, you have to realize that we are facing a mathematically impossible problem.
Impossible is a strong word.
But accurate here. The fundamental equation of quantum mechanics is the Schrödinger equation. In theory, if you solve it, you know everything about a system.
Okay, so why can't we just solve it for a piece of copper?
Because in a macroscopic solid, you have roughly Avogadro's number of interacting particles. That is 10 to the 23rd power.
Just to visualize that for you, that's a 1 with 23 zeros after it.
It's an unfathomable number of electrons and atomic nuclei, and every single one of those electrons is, constantly repelling every other electron.
Right, because they're all negatively charged.
Exactly. While simultaneously being attracted to all the positively charged vibrating nuclei, if you tried to write down the exact Schrödinger equation for a simple block of metal,
just writing it down.
Yeah, the equation itself would contain more terms than there are atoms in the observable universe.
That is just mind-bending.
No supercomputer, present or future, classical or quantum, can solve it rigorously. It is computationally and mathematically impossible.
So wait, if the math is literally impossible, how do physicists actually get anything done? When we have semiconductors, we have lasers.
We do,
Yeah.
and we get them by being radically pragmatic. Because we cannot solve the true many-body problem, the entire field operates on what physicists call toy models.
Toy models. I love that term.
It's the absolute meta theme of the textbook. A toy model is a deliberate, highly calculated simplification. Sometimes we strip away all the quantum mechanics entirely.
And just treat the solid using classical electrodynamics.
Exactly. Other times we use a semi-classical model. We treat the atoms as classical billiard balls, but the electrons as quantum waves.
And then sometimes you have to go full quantum topological. So progress isn't just about having a bigger computer.
Not at all. It's about having the intuition to know exactly which simplified model to use.
And knowing when that model is going to spectacularly break down.
That is the essence of condensed matter physics.
Yeah.
You isolate the behavior you want to understand, build a mathematical toy model, and aggressively test it.
Okay, let's unpack this with our framework. Let's start with chapter 1. Next.
Let us establish the baseline for how electrons actually move.
For chapter 1, mesoscopics in the electron phase, I'm going to set up your big idea. At mesoscopic length scales, which sit perfectly in the twilight zone between the atomistic scale and the macroscopic human scale, the quantum mechanical phase of the electron wave function becomes the absolute defining factor of how a material behaves.
That is a perfect distillation. We are looking at the exact boundary where quantum weirdness bleeds into measurable reality.
Where we have to stop pretending the electron is just a tiny charged particle.
Right, and start treating it as a continuous wave.
All right, let's move into our first advanced deep dive. To understand why this mesoscopic world is so wild, we have to start with the classical picture. The pinball analogy,
Yes, the Drude model.
right? Proposed way back in 1900. If you ask a random person how electricity flows, they'll describe little pinballs bouncing through a wire.
Paul Drude took the kinetic theory of gases, which worked beautifully for gas molecules in a balloon, and just applied it to a solid metal.
He just assumed electrons were a gas.
Essentially, yes. He imagined a fixed lattice of massive, positively charged ion cores with a gas of tiny electrons freely bouncing around inside.
And what makes them bounce around is just heat.
Right, thermal velocity. At room temperature, about 300 Kelvin, Drude calculated these electrons are zipping around at roughly 10 to the 5th meters per second.
That's incredibly fast.
It is, but it's completely random. They are scattering in every direction, so the net movement is zero. But when you apply an electric field...
Like connecting a battery.
Exactly. You introduce a slight, slow, directional drift to that chaotic swarm. That tiny drift velocity is what we measure as electrical current.
It makes perfect intuitive sense. It explains Ohm's law. But the textbook points out it's fundamentally wrong. Why did the pinball model fail?
Heat capacity. If electrons were truly acting like a classical gas, they should absorb heat energy just like a gas does.
But they don't.
Experiments showed that electrons in a metal contribute almost nothing to the specific heat at room temperature. Drude's model predicted a heat capacity roughly 100 times larger than what was actually observed.
100 times. That is a spectacular failure.
It was, and Arnold Sommerfeld had to fix it in 1927 by injecting quantum mechanics into the model.
Specifically, he brought in the Pauli exclusion principle, right?
Yes, and Fermi-Dirac statistics.
Let me make sure I have this straight. The Pauli exclusion principle says no two electrons can occupy the exact same quantum state at the same time. You can't just pile them all at the bottom.
Think of the available quantum states in a piece of metal like seats in a massive stadium.
Okay, I like this analogy.
At absolute zero temperature, the electrons want to sit in the lowest possible energy seats, right down by the field. But once a seat is taken, the next electron has to take a slightly higher seat.
You fill the stadium row by row, from the bottom up.
Exactly. And because there are so many electrons, Avogadro's number, you have to fill seats incredibly high up.
Right to the nosebleeds.
The energy level of the very highest occupied seat, at absolute zero, is called the Fermi energy. And this solves the heat capacity problem.
How so?
If you add a tiny amount of thermal energy to the metal, the electrons deep down in the lowest seats cannot absorb it.
Because to absorb energy, they'd have to jump to a higher seat.
But all the adjacent seats are already full. They're completely locked in place by the Pauli exclusion principle.
Oh, wow. They're literally trapped by the crowd.
Yeah.
So only the electrons way up at the top row at the Fermi energy have empty seats above them.
Precisely. Only that minuscule fraction of electrons at the surface of this Fermi sea can absorb heat or respond to an electric field.
That's crazy. Only the top-tier electrons matter.
And because they're sitting so high up in the energy stadium, they're moving incredibly fast. This is the Fermi velocity. In a typical metal, it's around 1,000,000 meters per second.
10 times faster than the classical thermal velocity Drude imagined.
And it doesn't drop to zero, even if you cool the metal to absolute zero.
Okay, so quantum mechanics drastically changes the speed limit. How does this change the way we build nanoscale devices? The book mentions two crucial length scales, the mean free path and the phase coherence length.
Right. The mean free path is the average distance an electron travels before it physically collides with something, like an impurity, and changes its momentum.
So that's the distance between pinball bounces.
Exactly. But the phase coherence length is purely quantum mechanical, because the electron is a probability wave, characterized by an amplitude and a phase.
The phase is like the ticking of an internal clock.
That's a great way to put it. The phase coherence length is the maximum distance the wave can travel while maintaining that synchronized tick.
Wait, back up. If the electron hits an impurity, doesn't that scramble the wave? Doesn't the bounce destroy the phase coherence?
It's a very common misconception, but no. If the electron hits a static impurity, a fixed defect, the wave scatters, but the event is perfectly elastic.
So the internal clock just keeps ticking flawlessly.
Yes. The wave remembers its phase perfectly after bouncing off a static wall.
So what actually destroys the phase? What scrambles the clock?
Inelastic scattering. Interacting with something dynamic, like colliding with another moving electron or scattering off a phonon.
A phonon being a quantized vibration of the actual crystal lattice. Heat, basically.
Exactly. When energy is exchanged, the timing is scrambled. This is called dephasing. So at very low temperatures, where thermal vibrations are frozen out, the phase coherence length can be hundreds of times longer than the mean free path.
The electron can bounce off 100 static impurities while remaining a perfectly coherent quantum wave. That's wild.
It really is. And this brings us to ballistic transport.
Right. What happens if we build a wire so incredibly short that its physical length is smaller than the electron's mean free path?
The electron wave travels entirely through the wire without bouncing off a single static impurity. It acts entirely like a ballistic wave propagating through a waveguide.
And the result of this is mind-bending. The textbook talks about a one-dimensional quantum wire, a quantum point contact.
A constriction so narrow that electrons pass through a single file.
The electrical conductance isn't a smooth variable anymore. It jumps in discrete, perfectly flat steps. It becomes perfectly quantized.
Yes, in steps of a fundamental constant, G0.
Which is 2 times the elementary charge squared, divided by Planck's constant. And the part I can't wrap my head around is that this value is independent of the material.
Completely independent.
It doesn't matter if it's ultra-pure gallium arsenide or silicon or a carbon nanotube. It's always an integer multiple of that constant. It's like the universe hard-coded a speed limit that ignores chemistry entirely.
It's a beautiful demonstration of how, at the nanoscale, macroscopic properties like electrical resistance simply dissolve.
But the quantum phase has a dark side, right?
Yeah.
It can completely stop transport in its tracks if the material is dirty enough.
Yes. Anderson localization. Philip Anderson won the Nobel Prize for this.
In classical physics, a dirty wire just has more resistance. The electrons slow down, but they get through. A dirty pipe still flows.
But because the electron is a coherent wave, if the disorder is strong enough, the wave scatters off multiple static impurities simultaneously.
And because they are static, the wave maintains its phase.
Which means the scattered waves can interact with each other. They interfere.
But why doesn't it just diffract around the impurities? How does a wave trap itself?
Think about destructive interference, where the peaks of one wave perfectly cancel out the troughs of another.
Right.
Anderson proved mathematically that in a highly disordered lattice, the multiple scattered pathways begin to interfere purely destructively in the forward direction.
So the wave's own reflections cancel out its ability to move forward.
The electron gets completely trapped, frozen in place by its own quantum interference. A material that should be a fantastic metal suddenly becomes a perfect insulator.
The phase literally builds a cage out of probability.
Yeah.
That is phenomenal. All right, that brings us to our connective tissue.
Let's hear it.
Understanding how quantum mechanics dictates transport perfectly sets up our next major topic. We've been looking at electrons just responding to static fields. What happens when we inject massive amounts of energy? What happens when these localized electrons are slammed by a high-energy photon of light?
That is the logical next step. But let us lock in the practical takeaways from Chapter 1 first.
All right, here is your practical recap. Number 1, the classical Drude model works perfectly fine for macroscopic wires, but completely fails at the nanoscale because it ignores the Pauli exclusion principle.
Which dictates that only a tiny fraction of electrons at the Fermi energy actually carry current.
Exactly. Number 2, in quantum point contacts, conductance abandons material properties entirely and perfectly quantizes based on fundamental constants. Number 3, strong disorder doesn't just slow electrons down. Anderson localization freezes them via destructive quantum interference, turning metals into insulators.
And here is your critical thinking challenge for Chapter 1. If you are designing a nanoscale circuit that relies on delicate quantum interference, how would lowering the temperature from 300 Kelvin down to near absolute zero fundamentally alter whether your circuit acts classically or quantum mechanically?
Think about what temperature does to those dynamic lattice vibrations. All right. Next,
Let us examine Chapter 2, interaction of light with electrons.
for Chapter 2, here is your big idea. Understanding optical properties requires a chameleon-like approach to physics. You treat light as a classical wave to understand how it travels, but as a discrete quantum particle to understand how it's absorbed.
This chapter is a masterclass in that toy model philosophy. You might assume you need the full, terrifying weight of quantum electrodynamics to understand how a mirror works.
But the textbook says that's counterproductive.
Let's get into the advanced deep dive. Why do we still use classical Maxwell equations for light? Isn't everything quantum at the bottom?
Everything is quantum at the fundamental level, yes, but macroscopic averages hide it perfectly. Think about a standard laser pointer.
You are not firing a single photon. You are dealing with trillions upon trillions of photons acting in concert. The statistical fluctuations completely average out.
So calculating individual particles is just computationally wasteful.
Exactly. Treating high-intensity light as a classical electromagnetic wave with the complex refractive index is perfectly sufficient to calculate phase velocity, refraction, and overall absorption.
But when we want to know why a leaf is green, or why silicon looks like a dark mirror, the wave model hits a brick wall. The chameleon has to change colors.
We have to zoom in and treat the material and the light quantum mechanically. We have to look at energy bands.
Right, because in a solid crystal, the discrete energy levels of isolated atoms smear out into continuous bands of allowed energy.
And crucially, there are forbidden zones between these bands, called band gaps.
In a semiconductor like silicon, you have the valence band, packed full of electrons, like the bottom rows of our stadium.
And above the forbidden band gap is the conduction band, which is mostly empty.
So a single photon crashes into the lattice. If it has less energy than the band gap, what happens?
The electron cannot absorb it. It's forbidden from existing inside the band gap. The photon simply passes right through the material.
Which is why glass is transparent. The visible photons don't have enough energy to bridge the massive band gap of glass.
Precisely. But if the photon does have enough energy, it gets absorbed instantly. It kicks the electron from the valence band up into the empty conduction band.
It's an interband transition.
And this transition builds the modern world. But we must look at what the electron leaves behind. A vacancy in the valence band. An electron hole.
I want to pause here because this trips up a lot of people. The textbook emphasizes that physicists treat this empty space, this lack of an electron, as a real positively charged particle. Why treat nothingness as a particle?
It's a brilliant mathematical shortcut. Imagine a sealed water bottle with a single air bubble in it.
Okay.
When you tilt the bottle, gravity pulls the water down, the water molecules flow downwards, and the air bubble moves upward.
The bubble floats to the top, yeah.
But the bubble isn't a thing. It has no mass. It is just the absence of water. Yet, it is infinitely easier to track the upward trajectory of one bubble than to calculate the complex fluid dynamics of a billion water molecules flowing around it.
Oh, that's a fantastic analogy.
In the valence band, instead of calculating a trillion complex trajectories of electrons shuffling to fill a vacancy, we calculate the movement of one single positively charged hole moving in the opposite direction.
So we have our excited, negatively charged electron in the conduction band, and our positive hole in the valence band. Opposite charges attract. The textbook says they can bind together.
Even though they are separated by energy, they exist in the same spatial crystal lattice. The Coulomb force reaches across that space,
They capture each other and orbit a common center of mass.
creating a bound state that acts remarkably like a hydrogen atom.
A positive hole and a negative electron. Artificial atoms synthesized using light.
We call this bound pair an exciton. It can move freely through the crystal lattice, transporting excitation energy without transporting net electrical charge.
Because the positive and negative cancel out. That is wild. But why do we care? How does this physics manifest in the devices we use every day?
Because managing these exact quantum transitions is the basis of optoelectronics. If you absorb sunlight to create an electron-hole pair and use a built-in electric field, a PN junction, to rip them apart before they bind,
You generate directional electrical current. A solar cell, harvesting quantum jumps.
precisely. And if you reverse it, inject an electron and a hole using a battery, let them find each other, recombine across the band gap, and emit a photon.
That's luminescence, an LED light bulb, or a semiconductor laser if you stimulate it coherently, the engine of the information age.
Exactly.
Which perfectly brings us to our connective tissue. We've seen how light and matter interact to create states we can harvest. But what if we want to actively isolate, engineer, and manipulate these delicate states to redefine logic itself?
The technological leap from classical to quantum computing. But first, the summary.
Here is your practical recap. Number 1. Physicists use a chameleon approach because classical models are computationally perfect for light propagation, but quantum models are required to understand absorption and emission. Number 2. Interband transitions are the microscopic engines driving the solar cell and LED industries. Number 3. Physicists treat electron holes as real positive particles which can bind with electrons to form excitons, acting like synthetic hydrogen atoms.
And your critical thinking challenge. Considering the exact energy required for an interband transition, why are some materials completely transparent to visible light while others are opaque or highly reflective? Think about the energy of a photon compared to the forbidden zones.
Next.
We step into the realm of ultimate control. Chapter 3, Quantum Computing, Qubits, and Decoherence.
For Chapter 3, your big idea. Quantum computers exploit superposition and entanglement to perform parallel processing on a massive scale, but their existence relies entirely on defeating decoherence, the leaking of quantum info into the environment.
This is a dramatic paradigm shift. As the text notes, quantum computing is not just Moore's law. We aren't just making silicon transistors smaller, we are changing the alphabet of computation.
Let's jump into the advanced deep dive. A classical bit is a switch, a definitive 0 or a definitive 1.
And a quantum bit, or qubit, leverages wave nature. It can be a 0, a 1, or a superposition of both simultaneously.
Described as a linear combination of probabilities. If you have a classical register of 30 bits, it stores one number. To test all combinations, you run it a billion times sequentially.
But a 30-qubit quantum register can represent all 1 billion possible combinations at the exact same time. It explores an exponentially larger memory space, a Hilbert space.
But the textbook clarifies a huge pop science myth here. A quantum computer doesn't just calculate all answers and instantly hand you the right one.
It absolutely does not. If you just measure the register randomly, it collapses into a random, useless answer.
You have to use quantum algorithms to manipulate the wave probabilities using interference, right?
Correct. You make the wrong answers destructively interfere, canceling out, while the correct answer constructively interferes, amplifying its probability before you measure it.
And that shatters classical limits. Let's talk about Peter-Shor's algorithm.
A classical computer relies on the fact that factoring massive prime numbers is mathematically hard. It takes an exponentially long time.
Which is the bedrock of modern internet encryption, like RSA.
But a quantum computer, using Shor's algorithm, finds the periodicity of the function exponentially faster. A large enough quantum computer could break RSA encryption in hours.
A complete security apocalypse. And love Grover's algorithm for searching unstructured databases.
If you are looking for one specific item in a list of n items, a classical computer takes n divided by 2 tries on average. Grover's algorithm finds it in the square root of n tries.
So for 1 trillion entries, a classical computer takes 500 billion tries. A quantum computer takes just 1 million tries. The speedup is staggering.
But building the physical machine is arguably the greatest engineering challenge in human history. You must satisfy the DiVincenzo criteria.
Let's go through those rules.
First, well-defined, scalable physical qubits. Second, reliable initialization to a perfect starting state. Third, universal quantum gates to manipulate them with extreme precision. Fourth, high-fidelity readout mechanisms.
And fifth, the hardest one.
The decoherence times must be significantly longer than the time it takes to perform your gate operations.
How do we actually build one of these qubits? The textbook focuses on solid-state devices. Superconducting circuits. The Cooper pair box. Now, a standard electrical circuit with an inductor and capacitor acts like a harmonic oscillator. Its energy levels are evenly spaced, like a ladder.
Yes, a parabolic energy potential. The gap between state 0 and 1 is the same as between 1 and 2.
Why is an evenly spaced ladder useless for a qubit?
Because of how we operate the gate. We flip the qubit using a specific microwave pulse tuned to the energy gap. If the ladder is even, that same pulse might accidentally excite the qubit from state 1 up to state 2.
The microwave just pumps energy in, it doesn't know where the electron is, you lose control.
You need an anharmonic oscillator. You need to warp the ladder so the gap between 0 and 1 is completely unique.
And to warp it, they rip out the standard inductor and replace it with a Josephson junction.
A microscopic slice of insulating material sandwiched between 2 layers of superconducting aluminum. The electrons bind into Cooper pairs.
Classical physics says the current should stop at the insulator.
But quantum mechanics says they can quantum tunnel through it, and tunneling is a non-linear process, making the junction a non-linear inductor.
That non-linearity warps the energy landscape. The rung between 0 and 1 is isolated, an artificial atom entirely controlled by microwaves.
To visualize this, physicists use the block sphere. Imagine a globe. The North Pole is absolute state 0, the South Pole is absolute state 1.
And the equator represents a perfect 50-50 superposition.
When we apply microwave pulses, we rotate the state vector around this globe. But keeping it there brings us to the ultimate enemy, decoherence.
The death of the quantum state.
The physical environment is constantly screaming at the qubit. Stray magnetic fields, temperature fluctuations, cosmic rays. The environment jostles the artificial atom. There's T1 and T2.
Energy relaxation, T1, makes sense. The qubit is at the same pole in state 1, loses energy to the environment, and falls back to state 0 at the North Pole.
But T2 star, or dephasing, is much more insidious. It happens when your qubit is in superposition on the equator. The environment slightly alters the qubit's resonance frequency.
The internal clock ticks too fast or too slow. The vector randomly drifts along the equator, losing its phase information and its quantum memory.
This destroys the superposition. But there is a genius engineering trick to fight low-frequency noise: the Hahn echo pulse.
I want to use an analogy here, a marathon race.
Let's see how this maps to phase.
All the runners start at exactly the same time, shoulder to shoulder, perfectly in phase. The gun fires, they run. But environmental factors, a headwind, a puddle, make them run at slightly different speeds. After 10 minutes, they're completely spread out. They've lost phase coherence, T2 star dephasing rate.
A brilliant analogy for phase spreading.
So we can't stop the wind. But what if, at exactly the 15-minute mark, you fire a second gun, and every runner must instantly turn around and run back toward the start at their exact same environmentally altered speed?
I see.
The fastest runner, who is way out front, is now at the very back, but catching up. The slowest is at the front, but being caught. Because they ran away for 15 minutes and back for 15 minutes, at exactly the 30-minute mark, every single runner crosses the starting line at the exact same millisecond.
That is a phenomenal conceptualization. In the actual qubit, we let the phase drift for a time due to noise. Then we apply a massive microwave pi pulse that literally flips the state 180 degrees across the Bloch sphere.
You literally trick the environmental noise into fixing its own error.
Yes. The same noise that caused the phase to spread now forces the vectors to perfectly refocus. This spin echo technique strips away low-frequency noise.
But high-frequency errors still happen. And in quantum mechanics, the no-cloning theorem says you can't just copy the data to back it up. If you measure it, you destroy it.
So we use quantum error correction, topological surface codes. We spread the delicate info of a single logical qubit across a vast array of physical qubits.
A tapestry of qubits.
And we only measure the protective ancilla qubits around the edges. By looking at their parity, we mathematically infer if an error occurred inside and correct it without looking at the data itself.
Checking the perimeter fence without looking in the vault. But the overhead cost. The textbook says to maintain a fault-tolerant error rate, you might need 10,000 physical qubits just to make one perfectly stable logical qubit.
The engineering challenge is immense.
10,000 to 1, which sets up our connective tissue. We just discussed ruthlessly isolating a single system. What happens when millions of electrons interact incredibly strongly with each other?
A fascinating pivot. Let us recap Chapter 3 first.
Your practical recap. Number 1. Quantum computing explores an exponentially larger memory space using superposition and interference, enabling algorithms that can break internet encryption. Number 2. Solid-state qubits rely on the nonlinear quantum tunneling of Josephson junctions to create controllable artificial atoms. Number 3. Decoherence is fought with control sequences like the Hahn echo marathon pulse, but ultimately requires massive error correction networks.
And your critical thinking challenge. If a quantum computer requires extreme isolation to protect phase coherence, how do you practically engineer a system that allows a user to rapidly write data in and read results out without destroying that very isolation?
Next.
Chapter 4. Correlated electrons in complex transition metal oxides.
For Chapter 4, your big idea. When electrons are forced so close together that they strongly repel each other via Coulomb interactions, standard models break down, resulting in emergent phenomena like high-temperature superconductivity.
Up to this point, we assumed we could figure out a massive solid by calculating the wave function for just one electron moving through a static, averaged-out background.
Let's get into the advanced deep dive. This assumption is the foundation of density functional theory, DFT.
Yes. It replaces the impossible problem of calculating 10 interacting particles with calculating how a single electron interacts with an average charge cloud.
And it works incredibly well for simple metals and standard semiconductors.
Because the electrons in those materials are heavily delocalized. Their kinetic energy, their desire to move is vastly stronger than their desire to repel each other.
But in transition metal oxides, like cuprates or manganites, that assumption fails completely. Why?
Because the electrons are highly correlated. Transition metals have active d orbitals and f orbitals. These are physically very small and tightly packed close to the nucleus.
So you're cramming negative charges into a tiny orbital, and the electrostatic repulsion goes off the charts.
The Coulomb repulsion overpowers the kinetic energy. The movement of one single electron instantaneously and violently affects the movement of every other electron in its vicinity.
Like a crowded stadium doing the wave. You can't predict the crowd by studying one person and assuming everyone else is a static blur. The stadium wave is a collective behavior.
An emergent phenomenon. The laws of the collective system are entirely different from the laws of the individual parts.
And because we can't simulate 10 strongly interacting particles, standard theories break down. The book mentions Mott insulators as a famous failure.
According to standard band theory, a material with a half-full energy band must be a metal. It should conduct perfectly.
Because there are billions of empty states right next to filled ones. But many of these oxides are perfect insulators.
Because band theory ignores extreme electron repulsion. In a Mott insulator, electrons are locked in a microscopic traffic jam.
An electron refuses to jump to a neighboring atom because there's already an electron there, and the Coulomb repulsion is too high.
So they all just refuse to move. The mutual repulsion creates an insulating state that standard quantum theory entirely misses.
And out of this complexity comes high-TC superconductivity, discovered in 1986.
Traditional superconductors only work near absolute zero, but these highly correlated copper oxide ceramics became perfect superconductors above the boiling point of liquid nitrogen, 77 Kelvin.
Where there's still massive thermal chaos. And the wildest part is, decades later, we still don't have a fully accepted theoretical explanation for the glue that binds them.
The math is just too hard. We also see colossal magnetoresistance in manganites, where a magnetic field changes resistance by thousands of %.
Which powered the read heads in early internet hard drives.
The ground state of these correlated materials is incredibly fragile. It's a chaotic balance of competing degrees of freedom, charge, lattice vibration, orbital shape, and magnetic spin. They fight for dominance.
Nudge one parameter and the whole system undergoes a phase transition, which sets up our connective tissue. If standard models fail and supercomputers choke on the math of Coulomb repulsion, we need a new mathematical language that ignores local details. That language is topology.
Indeed. But first, the summary for correlated systems.
Your practical recap. Number 1, models like density functional theory fail for complex transition metal oxides because they ignore intense Coulomb repulsion. Number 2, mutual repulsion can cause a microscopic traffic jam, turning materials that should be metals into perfect Mott insulators. Number 3, the delicate balance of competing degrees of freedom leads to unpredictable emergent properties, like high-temperature superconductivity, which we still can't fully explain.
And your critical thinking challenge. If emergent phenomena cannot be reliably predicted from first principles equations, how should an experimental materials scientist approach discovering the next high-temperature superconductor in a lab?
Next,
The Final Frontier of the Textbook, Chapter 5, Interactions and Topology for Itinerant Electrons.
your big idea. Topology sidesteps the chaos of interactions by classifying quantum electronic phases using robust, unbreakable integer numbers, meaning macroscopic properties become fundamentally immune to microscopic disorder.
This is a profound conceptual shift. Topology throws local details out the window and looks at the global, overarching geometry of the electron wave function.
Time for our final, advanced deep dive. What is topology? A classic analogy is a coffee mug and a donut being the exact same shape.
Mathematically, yes. Topology studies properties preserved under continuous deformation, stretching, squeezing, or bending.
Imagine a donut made of moldable clay. You can hollow out one side and mold it into a coffee mug without ever tearing the clay.
Because they share the same topological invariant, an integer. One hole. You can't have 1.5 holes. To change the topological class, you have to violently tear the clay.
But how does a coffee mug map to an invisible electron in a crystal lattice?
We look at momentum space, the Brillouin zone. When an electron travels through a periodic crystal, its wave function accumulates a quantum phase.
Like a clock ticking as it moves.
Physicists calculate what happens to the phase as you integrate it along a closed loop around this momentum space. They calculate a topological invariant called a Chern number, or a winding number.
The textbook uses the analogy of a piece of string.
Think of winding a string around a wooden pole. You can wind it once or twice. If you tie the ends together, the loops are trapped. You can slide them up and down, which represents introducing disorder. But the total number of loops is rigidly quantized to an integer.
And this abstract math has physical realities, like the quantum Hall effect discovered by Klaus von Klitzing.
You take a 2D sheet of electrons near absolute zero, apply a massive magnetic field, and the resistance doesn't change smoothly, it plateaus. The Hall conductance locks into exact, perfectly flat steps.
And the quantization is accurate to 1 part in a billion. It's the international standard for electrical resistance. But the mind-blowing part is that the semiconductor crystal can be dirty.
It can be filled with chemical defects and impurities.
In Chapter 1, we learned impurities cause scattering and destroy perfect transport. Why doesn't the dirt ruin the quantum Hall effect?
Because the macroscopic conductance in this state is physically tied directly to that topological winding number. The disorder is like stretching our clay donut. It changes the local shape, but the topological invariant remains unbreakable.
The topological index is a mathematical armor against physical disorder. The conductance can't degrade smoothly because the integer can't change smoothly.
Exactly. And this led to the massive discovery of topological insulators,
Which are entirely unique. Materials perfectly insulating on the inside, but their surfaces are perfectly conducting metals.
And it's not a normal metal surface. The surface conductivity is protected by topology. The electrons are fundamentally immune to backscattering.
So if an electron flowing along the edge hits a crater in the crystal, it doesn't bounce backwards and create resistance.
Its momentum is strictly tied to its magnetic spin. To bounce backward, it would have to physically flip its spin, which is forbidden, so it simply flows perfectly around the impurity without losing a single quantum of energy.
A material that guarantees perfect conduction on its surface, ignoring defects, and then there are composite fermions.
When you combine intense magnetic fields with strong Coulomb interactions, the electrons can bind with invisible quanta of magnetic flux to create new, emergent quasiparticles.
Which can act as if they have a fraction of an electron's charge, the fractional quantum Hall effect. Extreme correlation and topological geometry, synthesizing new physical reality.
Is stunning.
Let's look at our connective tissue. We started this deep dive with Drude's classical pinball electrons. And we end up using the abstract mathematics of continuously deformable geometries to explain why a dirty crystal conducts electricity with mathematical perfection.
It highlights the power of shifting our theoretical perspective when old models fail. Let us summarize this final chapter.
Your final practical recap. Number 1. Topology sidesteps impossible math by focusing on global geometric properties, proving global shape matters more than microscopic defects. Number 2. Topological invariants are strict integers that map directly to physical properties like conductance, rendering them immune to disorder. Number 3. Topological insulators feature perfectly insulating internal bulks surrounded by robustly conducting surfaces protected by topological rules.
And your final critical thinking challenge. If topological states are fundamentally immune to environmental noise and physical disorder, how might engineers use these materials to build a topological qubit that solves the massive decoherence problem natively in the hardware?
Next.
We have successfully completed the rigorous pedagogical framework.
Which brings us to our outro, an macro reality check. We've spent this entire deep dive submerged in the microscopic world. Anderson localization, excitons, Hilbert spaces, topological surfaces. But look around you.
Look at the macroscopic room you're sitting in.
Why don't we see these things? Why doesn't your coffee mug exist in a quantum superposition of sitting on the table and falling on the floor? Why is our day-to-day reality so relentlessly classical?
This is the profound, lingering mystery the authors touch upon at the end, the measurement problem, Schrödinger's cat. How is indeterminacy resolved by the universe?
Is it just decoherence? A coffee mug is trillions of hot, vibrating atoms bumping into each other, instantly destroying the quantum phase coherence before we can blink.
That is the most widely accepted view. But some theoretical physicists propose wilder ideas, like the GRW objective collapse theory. The wave function physically, literally collapses on its own.
Because of gravity, right. The idea that maintaining a heavy mug in a superposition of two physical locations would create a massive, conflicting difference in the actual curvature of space-time.
Theorists like Roger Penrose argue the universe cannot sustain a superposition of drastically different space-time geometries. Gravity forces the universe to pick a state.
Or, as the text speculates, is there a universal background noise destroying phase coherence everywhere all the time?
We simply do not know. The textbook provides the tools to master the solid state, but admits the boundary between quantum probability and classical reality remains one of the greatest open questions in physics.
So to our listener who challenged us to this intense framework, thank you. Next time you look at a solid object, remember, beneath its calm, classical surface is a raging, impossible storm of correlated electrons, topological winding numbers, and fragile quantum phases, all precariously balancing on the very edge of decoherence.
Thank you for joining us. Keep questioning the boundaries of reality and keep diving deep into the impossible.